Hello students, I am Dr.Pradyumna Mohapatra, Professor, Electronics and Communication Engineering, Vedang Institute of Technology. Today we will discuss DC biasing of BJT. In the previous class, already I told you what is DC biasing. The proper flow of zero signal collector current and maintenance of proper base emitter voltage is known as biasing. When you are going to bias a transistor, certain points we have to remember how to stabilize the Q point. So already I told you what is Q point. Q point is nothing but the proper value of the zero signal values of collector current and collector emitter voltage Vc, and how to stabilize Q point, that is important. To stabilize the Q point, if we will stabilize the value of Ic and Vc, that means we will get a proper amplified output. To avoid the clipping in output, means some of the part of the input signal and output signal, to avoid the clipping, we have to stabilize the Q point. How to stabilize the Q point? To stabilize the Q point, we go for a proper biasing methods. There are four biasing methods in a DC biasing of BJT. First, number one is your fixed biasing. After fixed biasing, then collector to base bias, that is, we may say that it is feedback bias. Then another biasing is your emitter biasing, and fourth one is your voltage divider bias. So we will go through one by one. We will go through details in each biasing. So then we will analyze the how far this biasing is, how far our Q point is stable or not by means of stability factor. So now today we will discuss fixed biasing of BJT, bipolar junction transistor. So this is your fixed biasing circuit of BJT. In fixed biasing, generally there are two resistors, one is your RB and this is your RC, and there is your plus VCC. Here there is a capacitors. In a DC, already I told you, in a DC the capacitor is open circuited because the reactance of the capacitor is infinity. So we can open circuit these two capacitors. So if we will open these two capacitors, if we will redrawing the circuit, so this one, this is your RB and this is your RC. Okay. First of all, we have to find out the input current. Input current is nothing but, in a transistor there are three terminals. This is your emitter, this is your base, and this is your collector. So this plus VCC is supplied to both input and output loop. This VCC here, this VCC is supplied both input and output loop. So this plus VCC, this with respect to ground, and this is also as input loop. This is your input and this is your output. So this, if we redrain the circuit for calculation, so this is nothing but like this. This is your same VCC. Same VCC is supplied to input and same VCC is supplied to output. So then, and this is your loop. First of all, this is your input loop and this is your output loop. In input loop, what we will find? We will find this is your input current, input loop, and this is your output loop. In input, we have to find out the input current. If we apply the Kirchhoff's voltage law, and we have to find out the input current. Input current is nothing but base current. So let us calculate the input current. How to get the input current? Input current is your base current. If I apply the Kirchhoff's voltage law to the input, so apply KVL, apply Kirchhoff's voltage law to the input. What is my input equation? So already I told you. So this is a emitter, base, and collector. In between base and emitter, there is a potential. We may say that this is your base emitter voltage VV. In a germanium or transistor or silicon transistor, if it is a germanium, the VV is 0.3. If it is silicon transistor, that is a 0.7. So here in base and emitter there is a potential you should take into account. This is your VV. Similarly, there is a collector and emitter. There is a potential. We may say that is your what? This is your VC. So apply Kirchhoff's voltage law to the input. If I will apply KVL to the input, this all potential is same. This is common grounded. So this is a closed loop. If I will apply the KVL, if it will go from plus to minus, then we will take minus. If we will go for minus to plus, then it will be plus. If it is a voltage, if that voltage, if there is a resistance, multiplied with the current. So according to Kirchhoff's voltage law, here there is a resistor. So what amount of current flow through this resistor? Because this is RB and this resistor is connected to the base. So obviously the current flow through the RB is your base current. So that is your IB. Base current is your nothing but is your what? Now IB. Here plus terminal and this is your minus terminal. The current flow through like this. This is your IB and this is your incoming and this is your outgoing. Similarly, this is your plus, this is your minus. So there are three things. One is your VCC, another is your IBRB, and there is your VB. If I will apply Kirchhoff's voltage law to the input, I will get what is my equation? Input equation. If I will apply KVL to the input, that is your what? Input loop. Apply Kirchhoff's voltage law to the input loop. Minus plus plus VCC. Again plus to minus minus current into resistance IB into RB. Then plus to minus minus VB equal to 0. If I will apply KVL to the input, I will get the input current. Input current is your base current. From this is your equation 1. If you want to find out the input current IB, then from this equation I can find out the value of IB. So IB value is how much? IB is nothing but VCC minus VB divided by what? That is your RB. Because VCC minus VB and minus IBRB bring to the right hand side, it will become plus and IB equal to VCC minus VB divided by RB. This is your input equation. To find out the input current, if you apply the KVL to the input, you will get the input current. Input current is your base current. Same VCC, already I told you, same VCC, this is a common VCC supplied to input as well as output. This is your VCC also and this is also what? Now VCC. If I will apply KVL to the output, apply KVL to the output, apply Kirchhoff's voltage law to the output. What is my output equation? So here minus to plus plus. What amount of current flow through the RC? Because this RC is connected to the collector terminal. Since it is connected to the collector terminal, the current flow through this is nothing but what? Collector current, that is your what? IC. So in a transistor there are three current. One is your base current, another one is your collector current, and third one is your emitter current. So emitter current is nothing but base current plus collector current. If I will apply KVL to the output, then what is my output equation? So minus plus plus VCC, here VCC, then here plus terminal and this here minus terminal, current entering plus, leaving minus. So IC into RC minus ICRC, then plus to minus minus VCE equal to 0 or VCE equal to VCC minus ICRC. Okay. So VCE equal to VCC minus ICRC. This is my equation. Let this is your equation 2 and this is your equation 3. So in fixed biasing method, IB here VCC minus VB by RB. This is my input current. After getting input current, you can find out the output current. So how to get operating point? Operating point means collector current and collector emitter voltage, IC and VC. IC and VC. Q point is nothing but IC and VC. So how to get IC? First of all, apply KVL to the input, find out the input current IB. After getting IB, you can find out IC or not, because IC equal to beta IB. As you know, collector current IC equal to beta IB. Beta is an amplification factor. In a common emitter transistor, IC by IB is your beta. So IC equal to beta IB. Once you got IB, after getting IB, you can find out the value of IC. Beta value is known, beta value is given. So once you get IB, then you can find out the IC, because IC equal to beta IB. So one operating point you can find out. Then find out another operating point, that is your VC. If you apply KVL to the output, you will get the output equation VC equal to VCC minus ICRC. Then you go for to check whether this biasing method is suitable for biasing or not. If I will choose this biasing method, my output means properly amplified output will get or not. So by means of stability factor, already I told you stability factor. What is stability factor? stability factor. Stability factor, that means to check whether the biasing method is suitable for a transistor biasing or not, can be judged by this stability factor. There is a general expression for the stability factor. For general expression for the stability factor, general expression for the stability factor. Already there are three parameters, ICEO, beta and VB. So in general expression for the stability factor, there is a formula or there is an expression SF equal to 1 plus beta divided by 1 minus beta DIB by DIC. This is your general expression for the stability factor. This derivation already I have already been derived this expression how to find stability factor, and this is a stability factor general expression for the stability factor SF equal to 1 plus beta divided by 1 minus beta DIB by DIC. So how to get DIB by DIC? In previous derivation here, how to get IB by IC? Here IB equal to VCC minus VB by RB. So after getting IB, then we calculate differentiating the base current with respect to collector current. If we will apply the KVL to the input, you will get the input current. This is the expression for the input current, IB equal to VCC minus VB by RB. How to get DIB by DIC? If you differentiate this IB with respect to IC, remember here VCC is a constant, maybe 10 volt, 20 volt, whatever supply we will provide, this is your VCC. VCC is a constant, VB is also constant because 0.3 for germanium and 0.7 for silicon, and the value of RB is also constant. RB is a resistance, some value of RB is given, maybe 100k, 100, maybe 200k, whatever our requirements, we have to choose the value of RB. So all values are constant. VCC is a constant because of supply voltage, maybe 10 volt, 20 volt, whatever the voltage we will provide, and VB is also constant, it is 0.3 for germanium and 0.7 for silicon, and then RB is also constant. Then whole value is constant. If I will differentiate this IB with respect to IC, then what is my DIB by DIC? What is my DIB by DIC? Because differentiating equation 2 with respect to IC, that is your DIB by DIC, DIB by DIC. The value will be what? 0 or not? Because IB equal to, in previous expression, input equation, IB equal to VCC minus VB divided by what? RB. This all values are constant. If IB is, the value of IB is constant, so DIB by DIC is 0. If this DIB by DIC is 0, if this DIB by DIC is 0, that means 1 minus the stability factor will be how much? SF equal to, that is your 1 plus beta by what? That is your 1 minus 0, that is 1, that is your 1 plus beta. This is your 1 plus beta. So stability factor in fixed biasing, that is your 1 plus beta. Already I told you, if the value of the stability factor is less, the stability will be more. With the value of stability factor more, that is this biasing method is not suitable for a transistor biasing. We will not get a properly amplified output because this beta value is vary from transistor to transistor. If beta value 100, stability factor is 100 plus 1. So this biasing is not suitable for transistor biasing. So because the value of the stability factor is as much as not lower, the stability factor is not decreases prominently. So we cannot choose this biasing method because of the stability factor. So in stability factor point of view, the stability is not improved in fixed biasing scheme. So we will go for another biasing. So another biasing scheme is, schemes are there. So maybe your feedback bias, or maybe emitter bias, or maybe your voltage divider bias. So this is your in case of fixed biasing scheme here. So all our values are here RB, and only there are two resistance RB and RC, and in these two equation, this is your input equation and this is your output equation. Using this input equation, you will find the IB by IC, DIB by DIC, and you will get the stability factor. The question may be asked in your examination, and maybe competitive or in your semester examination. This fixed biasing schemes are there. the value of RB, RC, VCC values have been given. You have to find out the unknown values. For example, so we'll discuss one by one example here in a fixed biasing scheme. So in fixed bias of bipolar junction transistor BJT, the value of RB is given. Suppose RB equal to 200 kilo ohm, RC equal to given, that is your 2.2 kilo ohm. Find IB, IBQ, ICQ, VCQ. Okay, and here VCC also given. VCC equal to 20 volt. VCC equal to 20 volt given. If the question not mentioned, that is your VB it is your 0.34 for germanium and 0.74 for silicons. So if VB not given, you may take VB equal to 0.7 volt, because in silicon transistors the leakage current is very less. So we can choose silicon transistor rather than is your germanium transistor. So how will get IB, IC and VC? So here also in previous, this is your figure. RB value given, RC value given, and VCC is given. How to find IB? IB equal to VCC minus VB by RB. Apply KVL to the input, you will get the input equation. From this input equation, you will find the value of IB. IB equal to VCC minus VB by RB. So already VCC given, VB given, RB given. We can find out the value of IB. So here, IB value is how much? So IB equal to IBQ. Q means about operating point. The Q point. It may be given, question may be given IBQ, or may be asked IB. So IB equal to, from equation 2, VCC minus VB divided by RB. All the value have been given here. VCC is your 20 and VB minus 0.7, because silicon VB equal to 0.7, and RB is your 200K, 200 into 10 to the power plus 3. So using calculator, here 20 minus 0.7, that is your what? 19.3 divided by, that is your 200. It is around equal to 0.096. 10 to the power 3, denominator 10 to the power 3. If we go to numerator, that is your 10 to the power minus 3 into 10 to the power minus 3 what? Ampere, or you may write here 0.096 milliampere. 10 to the power minus 3, we may write 0 milliampere. After getting IB, you can find out IC, because IC equal to beta IB. So IC equal to beta IB. Once you get IB, then you can find out the value of IC, because IC equal to beta IB. Beta is given 100, that is your 100 into, that is your 0.096 milliampere. So 100 means what? That is your what? That is your 9.6 milliampere. 100, if you multiply 100, the point value will be like this, 9.6 milliampere, that is your IC. So IB, already you find out IB, already you got IC, then another, that is your VC. If you apply KVL to the output, if you apply KVL to the output, here my output equation. If you apply KVL to the output, that is VCC minus ICRC minus VC equal to 0, or VC equal to VCC minus ICRC. So VC equal to VCC minus ICRC. Apply KVL to the output, here VCE equal to VCC minus ICRC. So here VCC value is how much? VCC value is your 20 minus IC is your 9.6, that is your 9.6. RC value is your 2.2 kilo ohm. RC value is your what? RC value here, RC value is your 2.2 kilo ohm. RC given, that is your 2.2 kilo ohm. So 9.6 into 2.2. This is your kilo ohm and this is your milliampere. IC is your milliampere. 10 to the power minus 3 into 10 to the power plus 3. That is your 10 to the power 0, that is 1. So 20 minus 9, that is your what? 20 minus, that is your what? 9.6 into 2.2. That is your 9.6 into 2.2. The value is how much here? 21.12. 21.12 volt. So that will be around what? That is your minus 1.12. So VCE, that is your minus 1.12 volt. So some parameters have been maybe varied here, RB value or RC value. So here VCE, it comes around minus 1.12 volt. That is your VCE. This is your VCE. So here we got IB equal to 0.96 milliampere, or you may like this, that is your 96 microampere. So in base current is in microampere, and collector current, that is your here milliampere, 9.6 milliampere, and VC equal to minus 1.12 volt. So VCE, if the question asks find VC and find VE. What is VC and what is VE? What is VC? What is VC? And this value, this is your collector. This voltage is nothing but VC. This voltage, this is nothing but VC. VC means what? From this collector point to with respect to ground, this is your VC. And VE, and this is nothing but, this is your emitter, this is your E. And this emitter potential at this point with respect to ground, this is nothing but VE. VC is nothing but this is your VC. And from emitter to ground, this is nothing but what? Now VE. VCE is nothing but VCE is nothing but VC minus VE. This is your VC and this is your VC. This is your VC or not? From this your collector emitter, there is nothing but what? Now VCE. This voltage is nothing but total voltage minus this voltage. Total from collector potential to this is nothing but VC. From emitter potential to ground, this is nothing but VE. And total minus this is nothing but VC. Similarly, VC is equal to VC minus VE. VE, how to get VE? This VE is nothing but, that is your grounded here. From this to this is nothing but 0. So VE is your 0. So VC equal to VC. VCE is nothing but VC. So in collector, in fixed biasing method, VCE is nothing but VE. VC is nothing but VCE. VCE what? VC equal to minus 1.12, say minus 1.2 volt. V value, VE is nothing but, that is your 0. Similarly, VBE is nothing but VB minus VE. Already I told you, VE is 0. Emitter potential with respect to ground, VE is 0. If VE is 0, then VB equal to VB. VBE equal to VB. In case of fixed biasing, it is already 0.7 for germanium and 0.3 for silicon. So next class we'll go through another biasing method, that is your that is your collector to base bias or feedback bias. So today we'll stop now. Next we'll meet again analog electronic circuit in your fixed bias, collector to base bias or feedback bias. Thank you.